Hey guys, I'm doing these videos by myself, so good luck with this. You guys remember where we left off? We were talking about the two different kinds of hypertension. The first one was called primary or essential hypertension, oftentimes referred to as idiopathic because it's of unknown origin. That's the type of hypertension we're going to focus on in this next section, talking about some of the pathology that's associated with primary or essential or even called neurogenic hypertension. The second type is obviously called secondary, and secondary hypertension is due to a number of secondary causes, which I've listed here. We're not going to focus on those because, like the name implies, secondary hypertension is secondary to some other dysfunction within the body. If you guys recall, this is where we left off. We were talking about the main determinants of blood pressure. Blood pressure is a function of cardiac output, the pumping action of the heart, and vascular resistance or peripheral resistance. We use this summary slide as kind of our framework for what we're going to do. If you look down here, blood pressure is a function of cardiac output and peripheral vascular resistance. And what we're going to do is we're going to go through in these next several videos some of these different causes for what causes vascular resistance or cardiac output to go up. The thing we're going to focus on first of all is some of the things that cause structural changes to the activity of the blood vessels, and then we're going to talk about some of the things that cause functional constriction, and then we're going to go back and talk about some of the possibilities of different mechanisms to increase both cardiac output and vascular resistance. For this video, I want you to recognize the role that sodium has. This is dietary sodium and the effect that it can have on the vascular system. So in this portion, I want you to remember two aspects. First of all, number one is this idea of sodium sensitivity. If someone's sensitive to dietary sodium, that when they eat excess sodium, the kidney, in order to filter that extra sodium, has to increase pressure in order to remove that salt load. That's the primary cause of sodium sensitivity. What we're going to also see in this video is there's a second mechanism that sodium may cause vascular changes or vascular hypertrophy that will increase vascular resistance. To illustrate the sodium sensitivity, I want to show you guys a paradigm here that has oftentimes been used to illustrate this phenomenon. So what you see here graphed is this is blood pressure of a series of different animals. In this experiment, they used rats, and they're monitoring their blood pressure over about 3 months. And then during this period of time, you can see this is mean arterial pressure. Mean pressure, a normal mean pressure is about 100 millimeters mercury. So in this group of animals, for the first about 55 days, they did 2 series of surgeries and monitored their blood pressure, doing an ambulatory style blood pressure. But what they did is they compromised the kidney function of these animals, and that mimics that phenomena of sodium sensitivity. So the first part of this illustrates the influence of sodium. So you can see at this time point, they switched the animals to what would be considered a high salt diet. And in this paradigm, they were using salt water as mimicking a high salt diet. And what you can see this, again, primary effect is blood pressure was normal until they switched to that high salt diet. And the illustration here is sodium sensitivity. The body has to increase pressure in order for the kidney to remove that salt load. And that's the phenomena of sodium sensitivity. About 35% of the American population demonstrates sodium sensitivity. And what that means is blood pressure elevates in order for the kidney to excrete that salt load. That's sodium sensitivity, and that's one aspect I want you to recognize. The second aspect that we're going to spend a bit more time talking about is the secondary effect of salt. And it's illustrated in this paradigm. They took these rats and they removed them from that high salt diet, and their blood pressure went back to normal. So illustrating again the influence of sodium sensitivity. The second part of this is illustrated in this vascular response. And what you see here is this group of animals, after they were switched to the low salt diet, their blood pressure went back down. When they went back on the high salt diet again, not only did their blood pressure go back up in a sodium sensitive manner, but the really important part here is that blood pressure continued to rise. And they actually stopped the study here, close to 100 days, because blood pressure in those animals was getting so high, you start worrying about secondary effects. So again, blood pressure went back up to normal, and then this continued rise is of some interest. And what we see happening there is that the blood vessels are changing in response to that. This is an important slide to illustrate that second effect. The blood vessels are becoming thickened in response to salt. So that phenomenon of thickening is called arteriosclerosis. Please notice that's different from atherosclerosis. Atherosclerosis is the accumulation of fatty plaque in the walls of arteries. This is a different phenomenon. Arteriosclerosis is where the blood vessels thicken in response to that high salt load. So what we see here is they're showing first and second hypothesis, but the pressure mechanism here to illustrate this was the salt. The salt causes an increase in blood pressure. That's sodium sensitivity, and that's an important aspect. The second part is shown here, that increase in blood pressure caused some sort of change in the blood vessels that caused that blood pressure to continue to rise. One hypothesis is simply that there's a tonic mechanism that causes blood vessels to thicken in response to blood pressure, but the second part of this is very important. I want you to pay attention to. This is called Fulcow's hypothesis, and it basically says with that increase in pressure, there is some highlighted here trophic mechanism that's causing that vascular hypertrophy. We're going to explore that trophic mechanism just a little bit later, because the importance here is that might involve angiotensin II. I know you guys are all familiar with the renin-angiotensin-aldosterone system. So just going back for just a second, sodium sensitivity causes blood pressure to rise so the kidney can filter that extra salt load. And then there's a secondary effect that causes vascular hypertrophy, and that vascular hypertrophy is probably associated with some growth factors. I mentioned IGFs here because we're going to talk about insulin later on, but then the role of insulin. Sympathetic activity probably causes that initial increase in blood pressure to cause the kidneys to excrete higher salt load. So the sympathetic nervous system, you guys are familiar with the sympathetic fight, flight, fight kind of response, but when we've talked about this, it involves both norepinephrine and epinephrine. We've talked about how that can influence the heart directly by binding to beta receptors on the heart and increasing cardiac output. Could also, this is primarily noradrenergic in the arterial tree, and then finally the kidney. But what I want to focus a bit more on is this role of the renin-angiotensin-aldosterone system. And the idea here is we're going to talk about how you can increase this angiotensin II load in response to the increased salt load. So what's being shown here, and you guys recognize this from before, I hope, that when blood pressure rises, the juxtaglomerular apparatus in the kidney senses that, causes the release of renin. Renin catalyzes the conversion of angiotensin into Ang1. ACE, or angiotensin converting enzyme, converts Ang1 into Ang2, and then angiotensin 1 causes thirst, angiotensin 2 is a vasoconstrictor, and then causes the release of aldosterone. Aldosterone, remember, is a steroid hormone from the adrenal medulla that has more long-lasting effects. Angiotensin causes water reabsorption, aldosterone causes sodium reabsorption, and both of those together helps to restore blood pressure back to normal. That's review. The new part on here is this idea that there are renal efferents. So remember efferents, that's coming from the central nervous system down to the kidney, to this juxtaglomerular apparatus, and that this is illustrating there are areas in your brain that are sensitive to sodium. So again, going back to this diagram, when you consume excess salt, there are areas in the brain that help increase that sympathetic activity, but there are also areas of the brain that are activating the release of angiotensin II, and angiotensin II may be causing that response. So that if we have these renal afferents active in the brain turning on this system, it's going to increase the production of angiotensin II. And then according to that Fulcow hypothesis, going back to this, Fulcow hypothesis says that angiotensin II acts as a trophic mechanism to increase the blood vessel thickness, causing arteriosclerosis, and that exacerbates the hypertension. So here we're seeing the renin-angiotensin-aldosterone system not just as a compensatory mechanism to control blood pressure, but also as a mechanism that may be causing hypertension. And if we go back to our summary slide here, what we're looking at down here is a change. Here we have the renin-angiotensin-aldosterone system, the sympathetic nervous system causing the effects on the heart, but then angiotensin also causing a change in structural hypertrophy. That's the important connection I want you to understand from this video. In later videos, we're gonna help fill in some of the rest of this. All right, so for that first part, make sure you understand the role of sodium.